Iya. Sebelum saya memulai, sebelumnya akan Molly informasikan terlebih dahulu pada sesi kali ini kita akan dibawakan full dengan bahasa Inggris ya. Jadi sekali lagi to all the participants who just join our study in the Netherlands online series, we are going to deliver this session in English. So for most of you who are from wherever you are, welcome to our special event study in the Netherlands online series. So this is really special because we are doing collaboration with Utrecht University, and the theme for today is Nanomaterial Science. Okay, so as usual, Molly is here as your host for today, and we have four speakers for today. Okay, I'm going to introduce them one by one, but before that, let's have like introduction from Nufik Neso Indonesia. Hold on 1 second. Let me share screen. It's not going to be too long because I believe that you are waiting for the main presentation from our speakers today. Okay, so this is our event study in the Netherlands online series Nanomaterials Science. So we have Egbert Mulder as a program coordinator Nanomaterials Science program, and then we have Adrian Duchdam from Institute for Nanomaterials Science, Detection of Microplastic in Ocean Water, Angela Mayhert's Institute for Nanomaterials Science, Inorganic Chemistry and Catalyst, and also Alicius Prockel from Nanomaterial Science, Physical and Colloid Chemistry, and myself, Molly, from Nufik Neso Indonesia. So this is just a short introduction about Nufik Neso Indonesia. So we just celebrate our 25th anniversary last week, so we're still happy, we're still over the moon, and then we're still tired, of course, with our back-to-back event last week. But again, we are here for you guys with this another special event from our like our regular event, right? Okay, so NESO Indonesia itself, Netherlands Education, we do have a lot of responsibilities. The first one, we facilitate NL knowledge because through this through this platform, we can hand in hand with our government between Indonesia and also Netherlands to collaborate with the events such as Week of Indonesia and the Netherlands Education and Research that we had last week. And also we support internationalization of education through these activities such as our online series and then online online counseling and also education fair that we always be there, especially this month. We got a lot of invitation from the institution, from schools, from university, so you have to join also the in-person event through this through the education fair. And we manage some scholarship as well, such as OKP LPDP Student Joint Scholarship, Orange Knowledge Program, and also Orange Tulip Scholarship that is going to be open next month. And also you share, this is the program that is really special that we collaborate with some of the university from Southeast Asia. Not only to invite the guys to the Netherlands, but also we invite the Dutch to come to Indonesia through Wilbeh program to study in Indonesia. And also after you finish your study, you can connect with NL Alumni Network because through this international network, you still can have the workshop, discussion, and a lot of positive activities. And I think the last one is the NL Alumni Career Fair. Next one. This is some of the practical information that if you would like to contact us, please do so. I think I'm just gonna try to inform that for the phone number is not really active anymore, but you still can, send our chat, okay, through the WhatsApp. And also, if you would like to talk with us, you can talk through online counseling from Zoom, okay? Our link is bit.ly/ojneso because our Zoom, we open from Monday and Tuesday from 3 p.m. until 5 p.m. and also from Wednesday and Thursday from 10 until 12 p.m., okay? And then all the digital brochure, of course, we upload already, and then you can download it through bit.ly/dbnufikneso. All the questions that have been compiled, you can access through bit.ly/FAQ Nufik Neso. Another interesting information. This is really, really huge. Okay, so you please come and join us. European Higher Education Fair, it's going to be held in Jakarta, 5 and 6 November, in Surabaya, 8 November, and also there is online event from AHEF, 9 November 2022. So I think from the Netherlands, we do have 22 institutions come straight away from the Netherlands to Indonesia, come to see you, and then to give you information more deep regarding studying in the Netherlands, and of course with the 22 institution from the Netherlands. Okay, you can access and then you can register free virtual.ehab.id. That's all the information that I would like to share with you guys. And now I have to give the floor to the first speaker. So we are here with Egbert. Hello, Egbert Mulder, as a program coordinator, Nanomaterials Science program from Utrecht University. Hello.
Yes, hello, good afternoon to you.
And then good morning to you. So welcome once again. It's really good to see you virtually. And I think it's time for you to give the information as well. So Egbert, so the floor is yours.
Thank you, Molly. Yes, good afternoon to you. It is just after 10 o'clock here in the Netherlands, and I will start sharing my screen with you and start my talk about the Nanomaterials Science program in the Netherlands in Utrecht University. So I'm the program coordinator, and the Nanomaterial Science program is supported by all the staff of the Bij Institute for Nanomaterial Science. And in my talk, I'm going to talk, of course, about the contents of the program. And Molly already told about the pitches from our PhD candidates who will talk about the research in the different groups of our the Bij Institute. And after their pitches, I will talk about the mission and applications and about scholarships. And of course, there will be room for asking questions. So what can you expect from us when you come to Utrecht University? We have a quite big team of more than 30 professors and about 120 PhD students who will guide you through the course program. They will support you in learning in the courses and, of course, help you doing your research in the different research groups in the Bij Institute. They are your supervisors, and they can help you whenever you have trouble getting further in your research or with your courses. Of course, we expect from you when you come to Utrecht that you are very motivated to become an independent researcher, maybe continuing in a PhD in the Netherlands or somewhere else. And that when things don't run that smoothly for you, you ask our help, because we also have a small team to support you. That's, of course, me as a coordinator to help you plan your studies. We have a study advisor who can help you with things in the personal sphere. And there's also Andrei Petrikov, who is also joining us today in this webinar, who is the program director and helping with other things. I hardly have to talk about the relevance of our program. I mean, chemistry is really the science to help our society forward in the development of a society not longer dependent on oil and gas, etc. And all the research groups and most of the research programs that are running in the Bij Institute have some connections with sustainability and a sustainable future for our planet. Of course, you can study nanomaterials in many universities in the world. And why would you want to come to Utrecht? I think Utrecht and the Bij Institute is a high-ranking institute for research in nanomaterial science and chemistry in general. Within the Bij Institute, we have a wide range of subjects you can study, from organic synthesis to nanophotonics, of which you will hear more later in this webinar. We, of course, have a matching course program And what is very special about our program that you can start research very early in the program. Even when you study in September, most of our students start their research already in the second period in November. That's because in the first year, you'll be taking courses and doing research side by side. So the dry facts about the Master of Science program in Nanomaterial Science, it's of course in English. It's a 2-year full-time program. Studying Nanomaterial Science is really a full-time job, I can tell you. You can start in September and February, and we receive about 45 students per year. So I will be talking about the content of the program, the freedom you have to design your own program, and about the community of the research groups in the Lebij Institute. The content of our program we like to say shortly as colloids, catalysis, and nanophotonics. And you see that also in our course program, which consists of a small amount of mandatory courses. Then you have 3 primary elective courses, and the major part, almost 3/4 of your program, you can spend on research. Partly in the research project, which is almost a year, and partly in the secondary elective courses, which you can spend on an internship, also doing research. And now I will go one by one by these different categories of courses. The compulsory course is the spectroscopy course, which starts in September. So if you start studying in September, you start with this compulsory course. We think this should be compulsory because spectroscopy is really the basis of all research wherever you go in the Lebij Institute. If you do either organic chemistry or nanophotonics, you will be doing some spectroscopy. The other course we call the academic context course, and this, yes?
Can I quickly, I don't think your slides are showing.
Oh, no.
I just noticed they froze. So can you maybe put them in presentation mode again?
Yeah.
Yes, so we see them, but they're not in presentation mode. So maybe try F5 or something.
Yeah, it's now I did F5.
You are sharing the wrong screen, I guess.
Oh, yeah.
Because we see the PowerPoint, but not the full slides.
Okay, I'll stop share and then I'll share again. So
no, we see PowerPoint, but not. Not.
Is this not good?
This is just open PowerPoint, but
yeah.
not the presentation. Not in the presentation mode.
Oh, that's strange. Okay, I'll go back. I saw a different screen here.
Yeah.
Okay.
Select another screen for sharing.
Is this
yeah.
the right screen? Yeah, yes. Is this the right screen?
Yes, looks like, yes. Thank you.
Okay. I don't know what went wrong, but sorry about this. So.
Yeah, it works.
Okay. So, excuse me. So I'll go back to this screen. So I've been talking about the different courses. So we have 2 mandatory courses, 3 primary elective courses, and the major part of your program will be doing research, almost a year in the research groups in the Lebij Institute, and possibly also half a year doing an internship somewhere else. So that's about 90% free choice. So spectroscopy, that's really the basis of any research topic you'll be doing in the Lebij Institute. So advanced spectroscopy is the compulsory course. And the academic context course is really about skills and attitude. So one of the things you'll be doing in this course is writing a research review. You'll be taught about, they will be teaching about responsible research and a few other things. So then about the chemistry course program, or I should be saying chemistry and physics, because many of the courses are about chemistry and physics. So this is our year program. Every course is taught once every year. And you see from left to right the 4 periods of our academic year. And you see in the first period, you recognize the advanced spectroscopy as the first course you will be taking when you start in September, as the compulsory course in gray. And the other colors are corresponding with the research areas I mentioned. Colloids are slightly yellowish. Catalysis, it's reddish, and nanophotonics is bluish. And you could say that every research group in the Debye Institute has about 2 courses, and those are the preferred courses to take as primary electives when you do research in their group. Always one of these courses is obligatory to take when you do research in a group, but that's only fair, I think. And most students also choose a second course taught by the same group. With this scheme, I also can explain that when you come to study and design your course program, you will be taking courses and doing research side by side. For instance, if you choose to do research in catalysis, and for instance, in Angela's group for inorganic chemistry and catalysis, you will probably be doing the advanced catalysis course in period 1 together with advanced spectroscopy, which is a full study load for that period. But in the second period, you might take microscopy, but not the second course. And that means that you will have time for one course study load to start your research. And then in the third period, you will be also taking a course of catalysis and also doing partly research in that period. And in the final period, in period 4, do only research. Then after that year, you will have done all your courses in the chemistry program and may have made a good start in your research. And so the rest in the second year, you'll be completing your research and spend the last half year of your program doing an internship probably. So that's about secondary electives. So I always advise my students to do an internship because it is a unique chance to learn about working in a company, for instance, or getting to know another culture by studying in a different country. Of course, you can also do extra courses from any of the other master programs in Utrecht University. And in a few cases, you will be needing to do some deficiency courses to meet entry requirements. So for internships, there are ample opportunities in the Netherlands and also outside the Netherlands. Most of the big chemical companies have factories and research institutes in the Netherlands like BASF, Dow Chemical, Shell, Sabich. You see them in the left-hand side of the screen. But our students are also very desired in other universities in other countries, because in our master program, you get a really good research education, a really good practical education in doing research. So students, universities abroad are always very happy to receive students from Utrecht University. Sorry. There's also another possibility to spend 30 credits of your secondary electives, and that's by doing a profile. For instance, if you're interested if you are interested in applied data science, there's a profile, but also for education, communication, and management. So about research, you will be hearing a lot more from our PhD candidates in a few minutes, but these are the 4 chemistry groups in the Bij Institute. There are also 2 physics groups, and there's even a possibility to do research in drug design in the chemical biology group of the pharmacy pharmacy department. So there's really a wide range of research subjects for you to do research in. And now I would like to share a video which we recorded 2 years ago. Let me see, where is my screen? Although I have to share this. 1 minute, please. Okay, share.
Hi everyone, I'm Eva and I'm a first-year student of Nanomaterials Science.
And I'm Do. I'm a second-year master's student of Nanomaterials Science.
We both do our internship at OCC, which stands for Organic Chemistry and Catalysis.
And here we are in David building where OCC lies. So now we are going to show you how's the life of OCC master's student in a day. So since it's Corona time, so whenever I go into the group, I need to do this check-in and check-out so that everybody keep track of how many people are here in the group at the same time. So this is my name. I just need to do check-in. Done.
So Tu, could you maybe tell us about the subject of your research?
So now I'm working with nickel complex and the alkyne coupling reaction with nickel complex, basically. And it would lead to the formation of alkene coordinated nickel complexes, which are pretty promising as a catalyst, I would say. So that's basically it.
Nice, and how did you pick this project?
So the thing is that I have a background in computational chemistry, and I was looking for a project that I can do both computational chemistry and experimental chemistry at the same time. And this project has some space for me to do experiments, and also I can do computational work. So it's perfectly fit with my goals, I guess.
Nice, and could you tell us about the successes and the disappointments of your research so far?
Well, yeah, I would say that success is yes. So I've known how to do stuff in the lab, and apparently I did successfully good synthesis. But also there's some disappointment, and that's the thing that always happens when you do research. You kind of have expectation for the result, and its turnout is not the same. So I kind of had some expectation of the desired product, but sometimes it just didn't work. But as a researcher, you need to accept that and overcome it, and then continue doing your work.
So Tu, which techniques do you use most in the lab?
So since I'm working with my nickel complex, which are air and moisture sensitive, so mostly I spend most of my time here in the glove box, where the amount of oxygen and water here is pretty low, so that I can work freely with my nickel complex.
Nice, and what kind of analysis do you use for measurements?
So for my analysis, I usually do NMR mostly, and sometimes I do GCMS to see what are the compounds in the mixture product. And sometimes I also use HRD analysis, which used for the crystal structure.
So what are the things that you do aside from lab work?
So beside the lab work, last year I need to do some courses within the program of Nanomaterials Science, but now that I'm done with the coursework, I still need to do I need to attend some group meeting or word discussion, and sometimes I need to work on my poster for a course within the program. So that's just basically it.
And what is the atmosphere like in the group?
Oh wow, yeah. The atmosphere in the group is pretty, well, I would say friendly, because I'm an Asian, so I come from an Asian country, and I thought that it would be difficult to get on well with people here, but apparently people make it feel like home, and people are very friendly, and then they really willing to help you out. So it's not like when you have a problem, you need to ask directly your supervisor. No, you can ask just other people in the group, and that is perfect. And also, I kind of like the atmosphere in the group before the corona, because we have a lot of fun stuff that we do together, like a birthday party or like cookies every Thursday, where you have to bring a cookie for everybody in the lab to have together, or weekly Friday borrow, which is kind of fun, and then you can have a chit chat with your lab mates, so it's basically fun. But now that it's Corona time, so it's changed a little bit, and we need to do the online meeting instead of physical one, so that's bad.
Yeah, and how has the coronavirus in general has influenced your studies?
The Corona had affected me apparently. So I've got 2 months delay for the Corona pandemic, and I need to do my literature review instead to keep track of the program. And also like my time at the lab is also limited because there's only like a limited number of people in the lab at the same time, so it's kind of annoying, I would say. But still, I think for now that people keep everything in control, so I can still work on my project, on my thesis, without worrying too much about not meeting the deadlines. So that's good.
What are your plans after you finish your internship and your studies?
So I'm kind of into doing research. So I think in the future I would want to pursue my PhD, and maybe not focus specifically on computational chemistry or experimental chemistry, but because I love both, so I would want to find a project that have both things, that just like what I'm doing with my master's thesis now. And that's basically the future plan that I want to do. So I just want to be a PhD then.
Nice.
Okay.
Je sais que c'est pas bien. Après 6 jours, j'en ai vaincu. J'y vais en solo intégral.
Okay. Let me see if I can find my screen back. Okay, it should be this one. Okay, is this visible again? Andre? No? Okay. Okay, it's here. Okay, that's better, eh?
Excellent.
Yeah.
Okay, yeah. Okay, we heard Nguyen Tu talk about her work in the OCC group, Organic Chemistry Catalysis, and she already told about the atmosphere in the group, that it was very friendly. So that when you start your research in the group, you're really quickly taken up as a full member in the research community. She talked already about outings and barbecues, etc., for the social atmosphere, and about the lunch lectures you regularly visit, and sometimes visiting professors from other universities come to work for a short time in the Debye Institute, and also give presentations. So it's really a very nice and friendly atmosphere when you are in a research group. So Nguyen too was thinking about continuing in the PhD position after her master's, and you see about 70% of our master students decide to do that, and others go directly to industry or into business or teaching. And these are the logos of chemical industries based in the Netherlands, where you could continue your career after your master. So now it's time for the pitches of our researchers, and I would like to ask Angela to share her screen with us.
Yes, thank you, Egbert, for introducing me. I will share my screen. Hopefully this is visible now.
Yes.
So yes, my name
is.
Yes, great. Well, my name is Angela Melgert, and I'm a third-year PhD candidate in the group of Inorganic Chemistry and Catalysis within the Bayer Institute and the Institute for Sustainable and Circular Chemistry. And myself, I live in Utrecht, and I studied here also for my bachelor and my master, and now I had the nice opportunity to continue with my PhD program in the same group as I did my master thesis. So I will share a little bit of my work here as my PhD, and also something I did actually during my master. So my project is on the thermocatalytic CO2 hydrogenation. And well, what we know is a lot of industries, especially the metallurgical industry, is known from its very big CO2 emissions, which in some cases are quite inevitable. And for us, the challenge to mitigate these emissions. So when we have this from point sources, we have them already quite concentrated. And we can also take this opportunity, use the electricity from excess sustainable sources like solar or wind power, and store this intermittent energy in chemical bonds. And in our case, we call this reaction like the power to chemicals. In our case, we want to react these CO2 emissions with sustainable hydrogen towards useful carbon compounds such as methane. In my case, I do this in collaboration with the metallurgical industry, and recently they developed an iron making process which already provides these quite concentrated CO2 streams in which we want to make them into value-added products. So we have this CO2 from a point source, and then in our first step, we want to convert this CO2 with sustainable hydrogen towards methane and water. And eventually, in a second catalyst bed, we want to further upgrade these chemicals towards aromatics, for example, to make even more value-added products. And my PhD is really focused on this first step. So how can we make good catalysts for the reaction of CO2 towards methane? So CO2 hydrogenation. So what is known in literature is that there are many catalysts that can do this reaction. What you can see is that there are a lot of noble metals, but also quite some base metals that are suitable for this reaction. And in particular, nickel has been studied as a cost-effective catalyst with high methanation activity, and also relatively high selectivity towards producing methane. But it's also an interesting reaction because even though you have a nickel catalyst, still you can tune and tweak its performance by, for example, the particle size. So what we know is that CO2 hydrogenation is a structure-sensitive reaction, which means that, well, size matters basically. So the size of your nanoparticles on your surface actually determine the performance, as not every atom on every aspect has the same catalytic activity. So how do we study this? How do you study how this works, how this performance? And usually what we do is we go in the hunt for the reaction mechanism, because what we think is if we understand the reaction mechanism, we can also, and we find the most efficient pathway towards the reaction pathway product, we can actually design a better catalyst. So for the CO2 hydrogenation reaction towards methane, there actually have been, there are 3 known reaction pathways possible. So we have the carboxyl pathway, the carbide pathway, and the formate pathway. And for studies on nickel, they've seen that the carbide pathway is a very suitable candidate. So in this pathway, we first have to reverse water gas shift of CO2 towards adsorbed CO, and then we have the further hydrogenation of CO towards methane on the surface. It can also go via the formate pathway. We can also call this like hydrogen assisted, because at first the CO2 needs to be hydrogenated before it can actually break the leftover CO bond on the surface. And actually, well, these are now presented as like separate pathways with what we think, and what's known from computational studies, which are very important to this research, is that there can also actually be an interplay between these pathways. So maybe you first have the direct dissociation towards CO, but then a hydrogen-assisted dissociation of the final CO bond to finally end up with your desired product, methane in our case. So what is the goal of my PhD? I want to find catalysts towards optimal CO2 hydrogenation towards methane. And I can tune this via various things. So I can use different metal nanoparticle sizes. I can change the support I'm using. I can use a titanium support or silica, which can have very different properties. Or I can even mix metals and in this way steer the reaction towards different products, selectivities, or activities. Like I said, we want to really understand the reaction intermediates. So we need some way of local intermediate sensing. And finally, as this is product in collaboration with the metallurgical industry, I also really want to understand what all these different impurities of this CO2 waste streams actually have an effect on the catalytic performance. And today I will focus a little bit on what I also did during my master's, and that's a bit on the support effects of this reaction. So what we did, we made catalysts, nickel supported catalysts on various metal oxide supports. So we have a silica, we have an alumina, a zirconia, a ceria, and a titanium catalyst, all with small nickel nanoparticles on top. And we have the reaction CO2 and hydrogen in a ratio of 1:4. And then we produce mainly methane and of course also water as a byproduct. But already looking at this graph, as you can see that the performance of this catalyst at 300 degrees is fairly different. And actually what we call the more reducible supports, so ceria and titania, perform already quite well at this 300 degrees. We also see that we actually not only make methane, but we also make some side products. So for example, you see some CO for the silica and alumina catalysts are quite high. So if you more desire to store CO, you can maybe choose those catalysts. And even though nickel is known to be a very good methanation catalyst, we actually see some CC coupled products for the ceria catalyst. So you see some ethane and some propane, which is also quite interesting because in the end, we would want to make also CC coupled products. So indeed, we see a higher activity for the reducible support at low temperature, highest activity for nickel titania, CO for nickel and alumina, and we saw some propane over nickel and ceria. But like I said, we not only want to find a good catalyst, we also want to understand why. And in our group, we're very focused on what we call operando spectroscopy. And operando really means looking at the catalyst at work. So we investigate what's happening on the catalyst surface, what kind of reaction intermediates do we see, and how can we correlate this to the activity. And what makes it operando is that in real time, we also check the products that are being made with, for example, a GC or an MS. And in my research, I mainly use operando infrared spectroscopy and also Raman spectroscopy. So how do we do this? So we have a lot of what we call our operando setups. And like I said, in my case, I use operando IR. So we have our reaction gases. First, we have to reduce our catalyst in situ with hydrogen, and we use some helium to dilute it. they go to our reaction cell, which is this big metal reaction chamber. So we first reduce it, then we introduce the CO2, and then the fun happens. We can see actually the reaction intermediates, and we have with our GC, we can also follow the products online that are forming. So for people who are a little bit less familiar with FTIR, I broke down our spectra in some different components. So first of all, we can see the gaseous species. So our two main products are carbon monoxide and methane. So here you can see also in the around 3000, you see them, the very specific CH stretchings vibrations from gaseous methane. And here this symmetric band around below 2200 is very specific for gaseous CO. So we can already use FTIR to already quantify a little bit the gaseous product we're forming. But of course, we are also very much interested in the reaction intermediates. So like I said, the carbide pathway with CO as a main intermediate is known in literature to be very important for this reaction. And indeed, in the region of 2000 towards 1700, we see different bands arising that we attribute to absorb CO on the surface. So and CO can be absorbed in very many different ways, so either linearly or in a bridged or multi-bound manner. So actually the CO is bound to different nickel atoms. And finally, we have some species from the hydrogen assisted pathway. So we see water, of course, which is one of the reaction products. And we also see the region where we expect formate or formial species. And we want to see, can we relate these intermediates to the catalytic performance? And yes, we saw some relations. So going down, we see all the different catalysts we made. And immediately what is seen is that the different reaction mediates actually are different for the different catalysts. A lot of things different. But the main thing we observed is actually this peak at 1590 to 1550, which is associated with formate, was actually shifting towards the right, so going towards lower energies for higher activity. And this was actually quite a significant shift. It's also changing in ratio. We think, yeah, maybe different source species are going on, or maybe this is a descriptor for the catalytic activity. So here you see it a little bit more in detail. In a previous paper of us, we correlated actually the CO bonding strength of different nickel particle sizes with the catalytic activity for nickel and silica. But now we could also see that for the different supports, maybe this CO descriptor was not enough, and we found this formate descriptor. So the bond strength of formate directly correlated with the turnover frequency, and the turnover frequency is basically how active your catalyst is towards methane. So we find these multiple spectroscopic descriptors, and that's what I do in my work. So can we use spectroscopy to elucidate these reaction intermediates? Can we find these descriptors, and in this way, can we also better design the catalyst for this reaction? So some small concluding remarks. So we found that reducible supports can be used to enhance methanation activity. And hopefully I showed that you can use FTIR as a powerful tool to elucidate reaction intermediates. So what's left for my PhD? I still do a lot of infrared spectroscopy. I also, like I said, I've extended to Raman and other spectroscopic techniques. I also want to study indeed what's the influence of all these impurities in these waste streams from the industry. Try different metals to accommodate these waste streams. And actually, I'm also really focusing on not different supports, but actually also the different phases and facets from supports and how these can further influence the catalytic reaction. I don't do this alone. We have a very big team in Utrecht University with a lot of technicians, collaborators from Leiden University, which makes working in Utrecht very fun and very nice to do. Yeah, so hopefully I've shown you a little bit of taste of my research, and I would be happy to answer any questions. Thank you for your kind attention.
Thank you, Angela. Molly, do we have time for a few questions, or do we
Sure
do
thing,
this
yes.
afterwards?
Of course. So if there is someone who would like to ask questions to Angela, please do so, okay? But if there is no question at the moment, I think we can, collect all the questions at the end, and then we can deliver all the questions to all the speakers then. But I can see now if there is some of the participants who would like to ask questions. Please do so. If there is no one, I think we can continue first with next speaker, Alessio, and then we can collect all the questions at the end. How about that, Egbert?
Okay,
Cool.
Alessio, please share your screen.
Now let's continue to Alessio. The floor is yours.
Perfect. I hope you can already hear me. I would also like to show you a bit of the research I've been doing at Utrecht University under the Nanomaterials program for my PhD. So I'm going to not talk a lot about catalysis, because that's not the only thing we do at the Utrecht University, but a bit more about physical and colloidal chemistry. So I'm gonna get towards the continuous flow and the bicontinuous emulsions. I'm gonna start out a bit simpler, just with a classical emulsion. If my mouse is also still working. Okay. I'm going to start out with a classical Pickering emulsion. So I hope you're all a bit familiar with this. So if we're in the kitchen and we take some oil and some water and we add these together and we mix them very, very vigorously, then for a short moment we will have these very tiny droplets of oil inside this continuous water domain. But very quickly, these oil droplets will coalesce, and then within a couple of minutes, we'll have these bulk layers of oil and water. So if we add colloidal particles and they're interfacially active, so they're of the right amphiphyllicity, they will attach to these droplets of oil, and they will form this dense shell around them. And thanks to this dense shell, if these droplets touch, they will not coalesce, and we have a stable emulsion. So a requirement for these particles to attach to the interface is that they're of the right wetting behavior. So depending on the contact angle they have with the oil and water, they can have enormous attachment energies of several 12,000 KT, thousands of KTs. They will attach to the film of this interface and they will jam it. So they're so strongly attached that they cannot be removed again. So what can we do with a Pickering emulsion, chemically speaking? So now I do get a bit towards the catalysis field, although it's not what I do my research on. If we have a Pickering emulsion and it has these particles on the interface, and we zoom in very closely, we can see we have a densely packed interface between oil and water. And if these particles are catalytically active, we can have a component A and a component B meet at the interface. They can react in the presence of the catalyst very rapidly and produce C and D. Now, this is done a lot in industry and it's a very rapid process, but it has one problem. We can continue to add component B and remove component D from the water phase because we can access this. It's the continuous phase. But for the components A and C, we cannot do this. These droplets are not connected to anything. We cannot simply add our reagents or remove our products. So what is then necessary is that the complete emulsion is destroyed, so we can harvest our products and we can add more reagents. But this is very time consuming. It can be very bad for the catalyst if we use different techniques to destroy this emulsion. For example, with magnetic nanoparticles, or we add an acid to render them interfacially inactive. Or we use very heavy particles and we centrifuge them very hard, or we use temperature-dependent systems. So let me fix it. Okay. So these processes are very much possible, but they're very energy intensive. And we can partially see that in the fact that almost half of the industrial energy use of the United States is not used in producing chemicals. It's used in separating them. So we can make them very efficiently, but then we have this mixture of chemicals. We need to destroy the emulsions again to get our products out. So what we would like to have is an emulsion that is not oil in water or water in oil. We would like to have an emulsion that is bicontinuous. And that is what I work on. So what I produce is a fiber, a bicontinuous fiber, which is made by squirting a precursor mixture into a bath of toluene. And if I take this fiber and I put it on the confocal microscope, which is a microscope which allows me to per slice in depth see what material is where in the fiber, we can see that it's a tunnel network of oil in a tunnel network of water. So we no longer have an inner phase and an outer phase. They're both completely connected to their respective flow phases. And yet it is still a Pickering emulsion. So if I dry the phases and I put them on the scanning electron microscope, then between the oil and water, we still have this layer of particles. So how do we produce this bicontinuous system? We start out with a ternary diagram. I hope you're medium familiar with, but I'll explain it a little bit. In this ternary diagram, we have a phase or a binodal curve. And if we're above this curve, we have enough alcohol, enough solvent that we can have the oil and the water mix. So if we're above this line, we have enough alcohol and we get a homogeneous system. If we're below this line, we don't have enough solvent and they phase separate. So if we take this green dot and we start out with that and we rapidly remove the solvent, we will get phase separation. And if we do that exactly in the green region, then we will go through something that's called spinodal decomposition, and it forms this tunnel-like structure. If we're too far to the left, we will get nucleation of the water phase. If we get too far to the right, we will get nucleation of the oil phase. So that is what we do using microfluidics. So we build these devices out of glass. So this is a 50 micron capillary in red and a 200 micron capillary in blue. And we flow the precursor mixture, so the mixture of the green composition to the red one and some toluene to the blue one. What then happens is that the solvent can very rapidly diffuse out of the precursor mixture and phase separation occurs. Now, I already told you about Pickering emulsions, and that's also very important in this case, because if we do this and we don't have any particles, phase separation will continue and we will get two bulk phases. But if we add particles, these particles will jam at the interface and they will rigidify it. So they will retain the bicontinuous structure. So with that system, we hope to do biphasic catalysis, but then continuously. So if we print these fibers, as I showed you before, in a container, we can flow component B through the length of these fibers and component A over the fibers. And we hope to do this continuously, and we can do this reaction. Now, unfortunately, these fibers are 50 micron in diameter, and it's very difficult to simply pump water through them. Why is this so difficult? Because water flows very difficult through narrow pores. So the pressure-driven system is much used all over the world because it works very well for large pores. And we can see this if we plot the velocity profile in a garden hose with a radius of 0.5 centimeter. And we can describe the velocity profiles with these formulas, then we will get very, very high flow speeds for a pressure of 1 bar per meter. But if we decrease the radius of the pores, so for example to 50 micron, we already get much slower flow speeds. And unfortunately, the biogel fiber we work with is not a 50 micron pore size. It is 50 micron diameter itself, but the pores themselves are much, much smaller. So in that case, if we apply this pressure, we get a flow so slow that we cannot sustain a catalytic reaction. So a physically chemical solution to this is electroosmosis. And I'm pretty sure most of you will not be familiar with that, so I'll very quickly explain it. So as you can see here, we have a pore with a silica glass wall. If we fill this silica glass capillary with water of a sufficiently high pH, the wall will be charged. As a result of that, there will be a charged double layer, which is free to move. If we then apply a potential over this fiber, we can induce a flow because we're attracting this net charge in the double layer. As a result, due to viscous drag, this will pull all the fluid through this fiber, and we can pump water. At the electrodes, we'll have solvent electrolysis to keep the entire system going. Unfortunately, the way we now produce the biogel fiber is at a very, very low pH. So here we don't have this charged wall, so we cannot have the flow yet. So these are some of the problems we then deal with during our research. So how do you measure the pH inside such a soft material? And how do you conveniently change the pH inside such a soft material? So one solution to measure the pH is to use the pH dependent fluorescence of fluorescein. So what we basically did is we let a pH indicator diffuse into the fibers, and then we used confocal microscopy, so fluorescent microscopy, to determine the pH inside of the fiber. To increase the pH itself, we added the base triethylamine through the oil phase of the fibers, and it can then diffuse into the fibers themselves. So what we can then do is we print a lot of these fibers, and in this case, I really printed a lot of the fibers, so we can macroscopically see the effect of the pumped water. We then apply a potential, and we can see that the bubble on the bottom is reducing in size, and the bubble in the top is increasing in size also now. Then of course we check if the moved water, so if the pumped water scales linearly with the voltage, and that is in case the case. So we're dealing with electroosmosis, and we're using the wall of the silica to pump the water through these fibers. And then afterwards we can see that still the bicontinuous structure, so the scaffolding of the silica is still intact. And of course, because we're dealing with an electrokinetic phenomena, we can see that the current that is being drawn by the fibers as they transport this water scales linearly with the implied potential. So now we not only want to have we don't only want to use our multimeters, and we want to take a look macroscopically, but we of course want to take a look at the fibers with the confocal microscope. So I printed a bit less fibers, and I had to change the liquid that surrounds them here, because normally we do these experiments in hexane, but as we're applying a potential and it's on a very, very expensive microscope, we don't want to have a solvent fire. So now they're in mineral oil, which is a bit less flammable. And then indeed we can see that if we apply a potential and we add a dye to one of the puddles, we can see that we're pumping this water through the fiber. Now, we want to be sure that we're not taking a look at just a regular enhanced diffusion process. So what is important is that the dye only flows from one side to the other, so that we have full control over the flow. So we added some dye to both the puddles, and we can see that that's the case. And what we can even do is if we add dye to only the left puddle, and the dye is being pumped through these submicron pores in these fibers, it's being released again on the other side. If we now zoom in a bit further, we can see that even the bicontinuous structure, because it's still an emulsion, it's a soft material. It's not a hard structure. It's an It's just two liquids with an interfacial scaffold. But fortunately, this also stays intact during electroosmosis, as well as the scaffolding I already showed you. So I've given you a bit of insight in what I do with physical chemistry and colloids. So we propose this reactor, which we hope to later during my PhD do by continuous biphasic catalysis. But we've already solved one of the big problems, which was getting flow inside of this reactor. We can pump some dyes through it, and what we've also done is that we've done some extractions of ethanol, so we can show that the chemicals can freely partition throughout these fibers. Of course, I've not been doing this research alone, which is, I think, one of the nice things about Utrecht University is that you always work in groups. You always work together, and you're never alone if you're facing a problem. So the work I've shown you, I've done together with the people shown now at the Van het Hof Laboratory, and I'll take any questions if you have them.
Okay, thank you so much, Alessio. So yeah, if there is a participant who would like to ask questions to Alessio, feel free to raise your hand. But if you feel like you would like to ask the question also through the chat box, again, feel free. Because we still have one more speaker, and then I think for now there is no question at the moment. So how about let's move on to Adrian to continue the presentation. So to Adrian, the floor is yours.
Yes, thank you very much. So let's see. So, do you see my slides?
Yes,
correctly?
very clear now.
Great. Well, thank you very much for that kind introduction. My name is Adriaan Duindam, and I do research on micro and nanoplastics here in Utrecht. So I'll start off with introducing the great team that works with me on this problem. And we grew a lot in the past few years, because I also did my master's thesis on this topic, and back then I was the only one, but now we have a lot of people working on this. So I'm working on the Polarisk project, which is part of the CASP cluster, which is a European cluster of 5 different consortia working on the micro nanoplastic challenge that we face at the moment. So Aurora is another cluster in which 2 of my colleagues, Laura and Laurens, both work. And then there's also the MEO Groot project where Jelle, Kirsten and Claudio are working on. And we also get a lot of useful data from our master students. At the moment, Hanya is working with us. So what are we exactly working on? As you all know, probably, plastic is a very useful and versatile material that we use in our daily lives. However, the waste management of plastic materials is not always sufficient to recycle all these plastic materials, which then means that they end up somewhere in the environment. For example, here you see a lot of plastic scattered across the ocean. And then the question that I and my colleagues are working on is, does this large amount of plastic have any health risks for humans or other living things? So things we specifically focus on are early life human health impacts. So that was the Aurora project that I showed in the earlier slide. Laura and Laurens are working on this. Plastic that litters and escapes into oceans. That is the main topic of the MEO Groot project, with Jelle and Kirsten working on it, as well as Claudio. And also another project, the Polar Explorer project, which I am part of, is the human exposure to MNPs, which is micro and nanoplastics, and their potential toxic effects. So basically, there's a large amount of plastics being produced, which end up somewhere, and this may lead them to fragment, and especially smaller plastic particles. This is where we we are interested about the health effects. So I want to make a distinction already between microplastics and nanoplastics. Microplastics being the plastics larger than 1 micron, and nanoplastics being plastic particles smaller than 1 micron. And as you can see here already, when we're talking about plastics, we can envision that a larger plastic piece fragments over time due to all kinds of biotic and abiotic influences into a smaller particle. But just to remind you that nano is not micro. So when we are talking about 1 10 micron particle, which is a bit thinner than a hair, we already have this huge particle, and the number of particles in the nanometer range that comes out of one of these particles is just immense. So even though these particles, these nanoplastics might be small, their number concentrations might actually be very, very, very large, which then of course also may pose a risk for us. No, we don't know yet, because at the moment it's still very hard to detect these particles, which is why we are working on the problem. So how are we tackling this problem? One of the things that we do a lot is, before looking at real life samples, is first synthesizing these particles ourselves so we control their properties. For example, colleagues have synthesized PVC particles, polyvinyl chloride, and stained them with Nile red, which is a fluorescent dye. Which then allows one to use confocal fluorescence microscopy, which basically highlights these particles stained with Nile red when examining, for example, cell culture exposure studies. And in these studies, cells, for example, white blood cells, but it can be any type of cells, are exposed to synthesized particles. And then because these particles are fluorescent, we can follow where these particles are in the cell culture. So it's possible to study uptake of these fluorescent particles, and also it's possible to then see if there are any toxic effects for these white blood cells, which in the end is relevant information when building a risk assessment. When talking about real life samples, sample workup is generally unavoidable. So it's really very hard to do to just get your microscope, look at the air around you, and then catch out the nanoparticles. There are a number of techniques we use. So concentration is nearly always needed. Sometimes filtration and concentration serve the same purpose at one, but it's often, because these samples are very dilute, needed to concentrate the particles. Another possibility is digestion, which means that around the particles that you want to investigate, there's a sample matrix still, which hampers your analytical technique, basically obscures your view of the particles. And then you can do all kinds of chemical or physical separation processes to try to remove this matrix from the particles of interest. And then lastly, what I've been working on a lot recently is filtration, which is sort of a concentration method, with the difference being that your particles do not stay in liquid, but are actually deposited on a flat surface. And this is nice for many microscopy techniques. And we do a lot of microscopy here at Inorganic Chemistry and catalysis, so that's nice for us. So again, these workup requirements are dependent on a number of films, the characteristics of your sample, the desired analytical technique that you want to use, and also on the size fraction of the analyte that you want to analyze. Then an example. So this is filtration of air. So the last one here, but then instead of a liquid, air has been blown through a gold-coated filter, gold-coated to ensure connectivity during these scanning electron microscopy measurements. And these samples were taken in the air around Utrecht near highways. And the aim was to to analyze the particulate matter in air, especially these particles below 10 micrometer, to see what they are made up of. And you see that the main component of this particulate matter is iron oxides, which could be brake material. Car brakes often contain a lot of iron. And there are also some other particles. By the way, this elemental analysis was done. So the picture you see is scanning electron microscopy, but the elemental analysis was done by EDX, which is energy dispersive X-ray spectroscopy. And I will explain a little bit more about this on the next slide. But for now, you can see that using this technique, we can basically image the particles, so we know their morphology. And with EDX, we can also assess their elemental composition. So most of the particles in air that we sampled, and this is of course a very small sample subset, but it's just to give you an overview, are inorganic, but there are also some organic particles. Some may be protein-like particles, but others could very well be plastics. However, as SEM-EDX only gives elemental information, a lot of polymers can't be distinguished from one another because they all contain carbon and sometimes oxygen, but only the elements does not give you the structural information that you're often interested in. However, SEM-EDX is a perfect technique to study a certain kind of microplastics, especially those relevant when sampling near highways, as they are very good for tire and road wear particles. So these particles are made from the abrasion from tires due to the friction between the tire and the road when driving. And they are considered microplastics because they basically their body is a rubber type of rubber, which is a polymer. But these particles are especially easy to recognize because next to the rubber core, they also have, and you can see this nicely in this backscattered electron image here, have these lighter regions represent particles encrusted in this rubber core with elements with a higher atomic number, which means they scatter more electrons, which is why they appear a little bit lighter. And these incrustations is already a morphological indicator that this particle might be a tire road wear particle, because basically little pieces, chunks of road are still encrusted in the rubber core of this particle. Another very nice marker for tire road wear particles, which you can easily observe with SEM-EDX, is sulfur, which is added during the vulcanization process in the tire manufacturing process. And also another compound that is added during this manufacturing is zinc. And if both of these elements are present, along with this morphology, it's very likely to say that this is actually a tire road wear particle. So I think this clearly illustrates that SEM-EDX is a very nice technique to do this, because it combines both the morphological and the elemental information that you need to be sure about the origin of particles when studying particulate matter in air. And you also see the maps here, the elemental maps of the marker elements, to show that they are indeed enriched in the region where the particle is. Then other types of samples. So I just showed you some air filtration, but we also do a lot of liquid filtration. And for this, we've been working a lot on special filter types from the Fraunhofer Institute from Halle in Germany. They are a partner in my consortium Polyrisk, and they produce filters with a very defined pore size, which is nice. And more important, a lot of commercially available filters are at the moment made of plastic particles. That's actually a very large challenge for us, because we, of course, want to do research onto plastic particles, often directly from the environment. And then it's very hard to defend that the particles that you find are actually from the environment when you use a lot of plastic materials within your lab. So a lot of our efforts actually go into designing procedures that are completely plastic free. This is filtration is one of them, where this was a big challenge. But now we have setups with silica filters with a pore size of 10 micron, and also for smaller filters made of alumina with pore diameters that are even below 100 nanometer, which is very nice because these filters are plastic free, but also have a very well-defined pore size. And then after the filtration, so you have a suspension of particles within the liquid and you filtrate them through these filters. We can do some more measurements, and that's where force microscopy comes in. You already see here, I think it's a little bit of a teaser picture, but I will explain this technique a little bit more on the next slide. So one of our main techniques for the discovery of nanoplastics, because the DX I showed earlier was lower microplastic, let's say, but for nanoplastics we use another technique called photo-induced force microscopy, which is basically a combination between atomic force microscopy and infrared spectroscopy. So the basic principle of atomic force microscopy is that you have a very small needle with basically an atomically thin tip, which taps along a surface. And while tapping, if this needle encounters a particle, there's a certain deflection up of the needle, and this deflection can be registered by an AFM feedback laser, which then gives you the topography of the sample. However, photo-induced force microscopy exploits another feature. So if you coat this tip with a noble metal, for example, gold, or also platinum iridium works, it's possible to also register the absorption of infrared light. So this works as follows. A QCL laser focuses infrared light underneath the tip with the coated, the noble metal coating. And when absorption of infrared light takes place on the sample, for example, by your nanoplastic particle, the dipole moment, which is basically the physical origin of the absorption of infrared light, the dipole moment in the sample changes. And because the tip has a coating of a noble metal, the tip may vibrate in resonance with this change of dipole. And when this happens, this resonance vibration is on a completely different frequency than the general feedback laser for the topography. So it's very easy to actually separate these two different vibrations from one another, which means that via the AFM feedback laser, you can distinguish both the topographical information that the photo-induced force microscope gives, as well as the absorption of infrared light on the sample, which is nice because usually infrared spectroscopy or microscopy is limited by the wavelength of the light, which means that it's very difficult to get a good spectrum of a high resolution with IR microscopy. But this PIFM method basically circumvents this and gives you IR spectroscopy with a nano resolution. This is very nice, and of course we also use this. So this is an example of work I did myself. I added polystyrene spheres, so this is polystyrene, by the way, the structure is shown, to blood serum, and then subsequently tried to detect back these particles. So I did a digestion basically removing the matrix. In this case, blood serum is mainly made up of proteins. So I did an enzymatic digestion as well as some hydrogen peroxide. And basically this digestion broke down the sample matrix, which then allowed me to image the particles that I added. So you can see here the topography map of the photo-induced force microscope, as well as the IR signal at 1490 reciprocal centimeters, which is a cc stretch of the aromatic ring of polystyrene and is characteristic for this polymer. So you can clearly see that the signal for this vibration is only present at the particles, and it matches perfectly with the topographical information. So it really shows that photo-induced force microscopy can be a very powerful technique in imaging nanoplastics from a digested sample, for example, blood serum in this case. Just to summarize a little bit, when you want to do nanoplastics analysis with force microscopy, you either get your sample, you get your sample, which can come from any kind of place, because actually people are finding out now that nanoplastics or microplastics are present at the most remote places, which again may indicate that it's time to hurry up with getting this risk assessment done. So you can get any type of sample. Generally, you still need to do a digestion, filtration, whatever. Then a pre-concentration step, separation into different size fractions, and then analyze this particle with both mass-based and number-based methods. So what I showed you just now was mostly microscopy imaging, which is a number-based method. And with these methods, it's most important to tackle a low concentration with, for example, pre-concentration, and also the statistical significance, because you can imagine one of the earlier slides I showed, that from one micro-sized particle, a lot of nano-sized particles are formed. So if you have a sample, it's already possible that there are billions of nanoparticles present in there, and it's basically way too time consuming to measure them all. So sampling in the correct way and then measuring in the correct way to ensure that your statistics are basically representative for the whole sample is a very important challenge for us. So, and outlooks things we are still working on. So these polystyrene spheres that I showed, we're still working with them to establish the validity of pre-treatment and preparation steps. And we're also working on the synthesis of other model particles, such as the example showed with the fluorescent dye added to the PVC particles. Spiked blood serum is still of interest, and we're also looking at spiked cell cultures and to see the toxicity effects. And more environmental samples are now, we're looking into bottled drinking water, people are looking into ocean water, and we're still also working on the method development, because we want to expand from just in microscopy that we just shown to also mass-based methods, because even though they don't give information on particle size or morphology, they do give the total amount of polymer present in the sample, which is basically a complementary piece of info next to the microscopy. I think that's it. I want to thank you for your attention, and if there are any questions, please feel free to ask them.
Okay, thank you so much, Adrian. So to all the participants who are still here, so if you would like to have questions to all the speakers, please do so. I think Andre, would you like to ask a question?
It's not a question. Hello. Since I missed the introduction, the beginning of this meeting, because we had an important meeting in the lab, presentation of my colleague who wants to develop batteries for electric cars, which can be charged in a matter of minutes instead of hours. pretty exciting project, so I had to be there. But I'm currently the director of the master program, and let me just say a few words that, I'm very happy to work at the university, in Utrecht University. We are often mentioned among the top 100 universities, like in Shanghai list, we are currently number 54. We are also among the first 10 or 20 universities in Europe, and the best in the Netherlands. Sometimes Leiden is put, depending on the list you're looking at. And Leiden, the famous Leiden University, is mentioned as number 1, and we are number 2, but sometimes we are number 1, etc. So it's an excellent university. It's a big university, which is also very nice. We are the largest of the Netherlands, and we have a lot of colleagues, a lot of research going on. We have a lot of interactions between different groups and between different people. And we welcome students from all over the world. And we are glad that, well, we have a rather diverse group of students with different backgrounds, and we are working hard to try to get it even more diverse and more, which makes student life is also more we find that also for our Dutch students, it's important that we have a diverse community of international students. So
thank you, Andrei. I still have some final slides.
Okay.
If I may.
Okay.
Yeah.
All right.
Do you see my slides now?
Yes.
Yeah. Okay. Put it in full screen. Still visible?
Not yet.
I think you need to share the presentation and not just your screen.
Yeah. Let me see how that is done. Let me see. Stop share, then share again. That's a bit silly that I don't understand how this works, but I'll just do it like this, no problem. You see the slide, so so some practicalities. So what do you need in your bachelor to be able to join our master program? So I look at 5 subjects in your bachelor curriculum. So these are physical chemistry, inorganic and solid state chemistry, spectroscopy, advanced organic chemistry, and quantum chemistry. And you need 3 of these subjects on an advanced level. So in a 3-year bachelor, that would be a 2nd-year level, and in a 4-year bachelor, that would be 3rd-year level. So if you comply with these criteria, you can apply for a position in our master's program. There are, of course, deadlines. For next September, the deadline is the 1st of April. But if you need a scholarship to study with us, you need to apply before the end of January. So then the deadline is for the application for the scholarships. And what scholarships do we have then? We have the Utrecht Excellence Scholarships, and there are very few. Last year there were only 3. So you need really to be top of your class if you want to apply for this scholarship, and it covers all the costs. So not only the fees, but also the living costs in the Netherlands. And then we have a smaller scholarship, that's the Holland Scholarship, that is 15K, just once for these 2 years. And you can also apply for that scholarship. Living in the Netherlands is pretty costly. I think for fees and living, you would have to reckon with 35 €. Per year, roughly. So if you haven't had enough of nanomaterials yet, you can always contact me and ask questions via email. you can chat with students online, and we have a masterclass in which 3 of our professors will present their research on the 22nd of September. It will be roughly the same time as we present today, this webinar. So it's from 10 to 1 local time, so it will be from 3 to 6 your time. So please join us. Please look at our website of the Nanomaterials Master Program for the data and the possibility to apply for this masterclass. It's not online yet, but it will come online in November. So that was it from me. If you have any questions, please.
Okay, yes, thank you so much, Egbert, and to all the speakers who already gave all the information regarding about nanomaterials and also the Utrecht University. So now I am going to invite to the participants. We do still have a bit of time. If you still have questions that would you like to ask regarding about the Nanomaterials Science or even the University of Utrecht. Okay. But okay, I think just to give one question, if there is no question from the participants, I think these questions can be answered to all the speakers, either Adrian, Angela, or Alessio. I'm just wondering one thing, because you guys talk about the nanomaterials and all the things that regarding with all the projects, but this is like a really simple questions. Which product on our daily life for sure already contain with nanomaterials? So who would like to answer the simple questions? Either Adrian, Angela, or Alessio, please go ahead.
So if I understand,
so I guess
Alessio, take the floor.
you can give a different example. So an example that's very often used at FCC for physical and colloid chemistry is paints. So basically all paints are engineered to have these nanoparticles in them, to have the specific colors, the specific drying characteristics, and the specific biofouling protection to last for years and years and years. So this is a product what's been designed with nanoparticles.
Right. Okay. So maybe Adrian, would you like to add something?
Yes. Well, my example may be a little less optimistic, because I'm of course doing environmental analysis, and well, I need to be more nuanced. So likely there are also in the air around you, the water you drink perhaps, nanoparticles present, nanoplastics. And my research then focuses on method development to detect these particles, which then in turn can be used by toxicologists to make a risk assessment. So I cannot immediately say that this is a depressing statement, because maybe they are good for you, maybe they rebalance your carbon household, and possibly there are health risks. But when you ask me to give an example of things containing nanoparticles, I'm afraid it's most things around us actually, with regarding the plastic side of things. But yeah. Could be good for us, could be bad for us. We just need to find out, because it might become a very relevant problem in the coming years.
Okay, then, thank you. Or maybe Angela, would you like to add something?
Well, for this question, I would always ask, like, what product has not seen a nanomaterial, right? I mean, I work in the field of heterogeneous catalysis, and almost all of our presentations start with the share of heterogeneous catalysis in industry. And I looked the numbers up right now, and I think 85% of all industrial processes use a catalyst, and of those 80% are heterogeneous catalysts. So yeah, our share of heterogeneous catalysts, almost every product you use every day, I think has seen a heterogeneous catalysis in one way. But I think the most known example, of course, is always your car catalyst, to at least make the fumes from your car not as toxic as they could be.
Okay, cool. Thank you. Thank you so much to all the speakers. And also, Egbert, maybe do you have any last information before we close this session?
No, just look at our website. There's much more information to read about the program, about the courses, the individual courses, what they are about. So if you're really interested, dive into our website. And,
okay, cool. Yep. Okay, so I think this is the very last one. So this is a question
There's
to
one question
Adrian.
in the chat.
Yes, there's one question in the chat. So a question
Yeah.
to Adrian. Can we use the same method to detect microplastic in fish and other marine animals, or require certain treatment? So this question is from Aslan. There you go, Adrian.
Yes. Yeah, good question, Aslan. So actually the example I showed of the spiked blood serum, where I recovered polystyrene spheres that I put in myself, basically to develop a method. This blood serum came from a harbor porpoise. I always struggle with the word, but it's a small, it looks like a dolphin, but it's not. It's a small marine whale that lives, for example, in the North Sea near the Netherlands. And in this case, the workup worked, but the general idea is when you want to detect microplastics in fish or other marine mammals is that you will need a digestion to remove tissue or blood, depends on where you are sampling. So you will need to digest a lot. And then the question is, how much plastic did the fish take in? Because it might also be necessary to then do pre-treatment steps to concentrate the sample. And then the question is, how much of the particles did you lose in your process getting there? Because it's very optimistic to say that you don't lose anything while doing a digestion or pre-treatment. But then again, it's very important to when developing these methods to already look out for these things. So you can get a recovery rate from a filtration, for example. But yeah, in principle, the methods we are developing are also applicable to fish or marine mammals. But we're not there yet.
Okay, there you go. Thank you so much, Adrian. Hopefully this question already answered. So thank you for asking for the question. I think that's all for now. We already reached the time. And then once again, I would like to say thank you to Egbert, Adrian, Alicia, Angela, and also Andre from Utrecht University. Thank you so much for join us with the Study in the Netherlands online series for this time. And yes, hopefully we can see each other in person next time. And then to all the participants, thank you so much. And then if you missed out this online event, we are going to upload this video by the latest tomorrow on our YouTube channel. So my name is Molly. I'm signing off. Once again, thank you and goodbye.
Bye. Have a nice day.